Steady-state simulations require accurate pump curve characteristics, particularly in the normal zone of operation. What do I mean by accurate? This lesson will progressively answer that question. I will begin by demonstrating how to check the suitability of your steady-state pump data. Let's look at the data available for the steady-state pump curve. Selecting a pump with a right click and selecting Edit, here we can see the 3 points defining the pump's flow, head and efficiency curves. Now let's look at this data as a graph and compare it to the pump type data that will be used during steady state and transient analysis. You can view a graph of the pump's curves by right-clicking the menu, selecting Graph Pump Type. This provides access to the pump's torque curve characteristics and head curve characteristics. The green line represents the pump's characteristics that will be used in transient simulation of the normal zone plus the reverse speed dissipation zone. The red line is the pump's characteristics used for transient simulation of the dissipation zone. The blue line is the characteristic curve used for transient simulation of the turbine zone. I'm going to use this slider to adjust how much of the reverse flow zone graphs are visible. In fact, I'm going to hide all of those zones. Now let me use this slider to show less of the positive flow zones. Focusing on the normal zone of operation, it becomes clear that overlaid on the head curve characteristics are 3 points showing the rated point, low flow point, and high flow point specified by the user. The dotted black curve between these points shows the parabolic interpolation applied to real-time and steady-state simulations. Assuming the 3 points used to define the pump's steady-state flow head curve are taken from manufacturer's data, we can consider these 3 points, the open black boxes, as accurate. The question remains, however, are they the best 3 points to produce accurate real-time and steady-state simulations? Comparing the dotted black line to the 3 black box points reveals how closely steady-state simulation will match the manufacturer's pump curve. The software's parabolic interpolation will always match the low flow and rated flow points exactly. How well the high flow point matches the dotted interpolation curve depends on 1. Whether the real pump curve has a parabolic shape, and 2. Where the user chooses to place the low flow data point on the real pump curve. The green line in this example is a very close match to the real pump curve, so we can use its shape to form judgments about the accuracy of the dotted black line used for steady-state simulations. To further explore the subject, let's introduce the system curves for this pipeline. The model is of a simple pump pipeline with a tank at both ends. Consequently, water level variation in each tank is the only variable, apart from pump flow rate, that changes the system curve. The software has been previously used to generate system curves for the extreme water level cases. Those system curves have been stored as files in this jobs folder. I can display those files using this button and select them here and give them useful names. I'm going to call this one best and this one I'm going to call worst. Now ticking this box to show the system curves. The system curves reveal that the pump running at full speed will operate only over a very narrow band of flows. Okay, back to the topic of accuracy of real-time or steady-state simulations. Observe what happens when I shift the low flow data point, which is currently at 4.4 litres a second, to near the worst system curve by closing the graph and editing the pump's data and putting the low flow point at 8.8 litres a second, 310 metres head and 74% efficiency. Okay, back to the graph. Note that the dotted black line within the range defined by the system curves. It is now tightly matched to the green line, which we can use to judge what the real pump curve looks like. We can now expect accurate steady state and real-time simulation results. Before ending this lesson, note the other slider at the top of the form. It allows you to shift the transient pump curves to a different pump speed, 100% being the full rated speed. This provides a useful way of assessing pump operation at lower speeds. For example, in this system we can conclude that the pump will only deliver flows at speeds of 81% and higher. For example, that has introduced you to reviewing the accuracy of real-time or steady-state pump simulations. The key messages are: 1. Generate the system curves and display them over the pump curves. 2. Place the pump's low flow data point slightly outside the flow range the system will operate within. 3. If necessary to improve accuracy, shift the rated point inside the pump's operating range and place the high flow data point just outside the flow range the system will operate within. 4. Wherever possible, keep the rated points values as the real pump's best efficiency point values, because the software uses the rated point to estimate a pump's moment of inertia. And 5. Do your accuracy checking at pump full speed.